The universe, a stage of unimaginable scale, where stars perform their dramatic lives over eons. We've come to expect their grand finales, the spectacular supernova. These cosmic explosions, so bright they can briefly outshine entire galaxies, are the fiery death throes of massive suns, scattering the elements vital for future stars and planets across the cosmos. It's a violent, glorious end. A known process. A predictable, albeit devastating, event. But what if a star, a truly colossal sun, simply vanished? Not with the expected, universe-shattering bang, but with a baffling whimper. One day, it's a beacon, shining with incredible luminosity from about 75 million light-years away. The next, it's gone. A profound absence. Scientists were not just surprised, they were baffled. There was no supernova. No brilliant, blazing death announcement. Just an unnerving silence. This is a story that challenges our most fundamental understanding of the cosmos. Our cosmic detective story begins in the Kinman Dwarf Galaxy, a modest collection of stars located roughly 75 to 80 million light-years from Earth. It's a distance so vast that we cannot resolve individual stars with conventional telescopes. Yet, we can detect their unique chemical signatures, imprinted within the galaxy's overall light spectrum. And it was within this archival data, collected between 2001 and 2011, that astronomers first identified our central figure, a luminous blue variable. This luminous blue variable, or LBV, was a true titan, shining with the intensity of approximately 1 to 2.5 million suns. LBVs are the rock stars of the cosmos, incredibly massive, intensely luminous, and famously unstable. They live fast, burning through their fuel at an extraordinary rate, and are prone to violent, unpredictable outbursts. This particular LBV showed all the telltale signs of being in the chaotic, final stages of its life. Astronomers eagerly anticipated its grand finale, expecting a supernova within years. Then came the fateful observation in 2019. An international team of astronomers aimed the European Southern Observatory's Very Large Telescope, a formidable instrument, directly at the precise coordinates of this anticipated cosmic event. They were hoping for an update. Perhaps a precursor to the supernova. Instead, its distinct spectral signature was gone. An object that had been millions of times brighter than our own sun, a celestial beacon, had effectively vanished. Without a trace. The stage was empty. This is where our cosmic crime story truly intensifies. For a star of this immense mass, its death warrant is practically pre-signed by the laws of physics. The crushing gravity in its core wages a constant, desperate battle against the outward energy generated by nuclear fusion. When that nuclear fuel eventually dwindles, gravity inevitably wins. The core collapses catastrophically, then rebounds in a titanic shock wave that should, in theory, obliterate the star. This process, we know, is a supernova. A supernova, especially from a star this massive, is one of the most violent and energetic events in the universe. While not an absolute guarantee of detectability from 75 million light-years, a typical explosion should have been observable. Astronomers meticulously scoured the data, searching for the telltale afterglow, any residual light from this cosmic explosion. They found nothing. No flash. No fading light. Just a void, a patch of sky where the distinct signature of a behemoth once roared. A profound, unsettling emptiness. It's the astronomical equivalent of a colossal skyscraper imploding directly into its own foundation, without making a sound or kicking up a single speck of dust. The sheer absence of the expected, colossal explosion was far more puzzling, and frankly, far more unnerving, than the star's mere disappearance. This anomaly challenged our very ideas about how the biggest, most massive stars meet their ultimate demise. It demanded an explanation. A new hypothesis. In any good mystery, you first eliminate the simple explanations. So, what could have happened to our vanished star? The leading, least exotic theory proposed that the star wasn't truly gone, but merely hiding. Luminous blue variables, like our missing subject, are renowned for undergoing massive, violent eruptions where they shed enormous amounts of their outer layers. This process creates a thick, opaque cocoon of dust and gas around the star, potentially blocking its light from our view entirely, transforming it into a much fainter object we simply couldn't detect. This hiding explanation is a perfectly reasonable scientific possibility, and it's important to state that the fate of the Kinman Dwarf star officially remains inconclusive. The investigation is open. But this perplexing case opened a door to a far more profound and unsettling idea. What if the star didn't just hide? What if it truly, unequivocally, was gone? What if the star didn't explode in a supernova because it imploded, entirely and silently? This brings us to the prime suspect in our cosmic investigation, a phenomenon known as a failed supernova, or more precisely, a direct collapse. The physics behind it are both elegant and terrifying. In the dying heart of a massive star, the core collapses under its own immense gravity, generating a huge burst of invisible particles called neutrinos. In a successful supernova, a powerful rebound shockwave uses this energy to blast the star to smithereens, creating the brilliant explosion we expect. But in a failed supernova, that crucial shockwave stalls. There isn't enough outward oomph, or the star's own gravity is simply too powerful, too relentless. The outward push fails. And with nothing left to halt its inexorable descent, the star's immense gravity completely takes over. All of that material just keeps falling inward. The star essentially swallows itself, collapsing past the point of no return to form a black hole directly. There is no glorious explosion. No final blaze of glory. The star just goes out. Its light and matter snuffed from the visible universe in a silent, gravitational freefall. A quiet, invisible death. A good detective, however, needs more than one piece of circumstantial evidence. The vanished star in the Kinman Dwarf galaxy is a compelling cold case, certainly, but it's not definitive, irrefutable proof of a failed supernova. To truly build a robust case for this radical new theory, to turn the suspect into a convicted phenomenon, we need to look for other clues. We need corroborating evidence from across the cosmos. Have other massive stars pulled off this silent disappearing act? And we have found them. Or at least, strong candidates. One famous example is a star known as N6946bh1, located in a galaxy 22 million light-years away. In 2009, this star suddenly brightened, then began to fade, and by 2015, it had completely vanished from optical view, also with no detectable supernova. This suggested that the Kinman Dwarf case wasn't just a unique, baffling anomaly. This silent end might be a recurring, hidden cosmic event. However, the story of N6946bh1 has since gotten more complex. Recent, incredibly precise observations from the James Webb Space Telescope, with its unparalleled infrared vision, revealed that what we initially thought was a single star was likely a blend of at least 3 distinct objects. This new data suggests the event might have been a stellar merger, rather than a single star's disappearance. So, while N6946bh1 remains a candidate for a failed supernova, it's no longer the clean, straightforward piece of evidence we initially hoped for. The mystery deepens. Perhaps the most powerful, and indeed, the most damning evidence, the true smoking gun in our cosmic investigation, comes not from a star that vanished, but from a black hole that appeared with suspicious quietness. Astronomers discovered a remarkable system called VFTS 243, a binary pair featuring a massive, living star and a black hole companion, locked in a tight, gravitational dance around each other. This perfect pairing holds a vital clue. Here's the critical piece of evidence: when a massive star dies in a messy supernova explosion, the resulting black hole often receives a powerful innatal kick, a recoil sending it flying through space. This kick typically knocks its binary orbit into a lopsided, highly elliptical shape. But the orbit of VFTS 243? It's almost perfectly circular. The black hole is moving as if it was born without any violent kick at all. This near-perfect circularity is one of the clearest indications we have that the star which formed this black hole did not explode. It likely collapsed entirely, silently. A quiet birth. So, what does this all mean for our understanding of the universe? This isn't just about one or two weird stars. This silent stellar death is about significantly revising fundamental parts of astrophysics. First, our census of black holes is probably fundamentally wrong. For years, our estimates of black hole populations were intimately tied to the observed rate of supernovae. But if a significant number of black holes are born in this quiet, invisible manner, the universe could be teeming with a vast, hidden population of them. Some theoretical models, bolstered by the puzzling lack of observed supernovae from the most massive stars, now suggest that anywhere from 10 to 30% of massive stars might end their lives this way. This could elegantly explain some of the unexpectedly massive black holes that gravitational wave observatories have recently been detecting. These silent collapses are not just theoretical curiosities, they are a profound, hidden mechanism shaping the dark architecture of our cosmos. They're telling us a crucial piece of the cosmic story we've been missing. Second, this silent demise changes our understanding of the cosmic recipe itself. It was once a common simplification that supernovae were the primary factories, forging virtually all the heaviest elements in the universe. While supernovae certainly create many elements, we now know that other catastrophic events, especially the violent mergers of neutron stars, are a dominant source for the absolute heaviest stuff, elements like gold and platinum. If up to a third of massive stars don't explode and spread their newly forged elements, it forces us to rethink precisely where the building blocks of planets, and indeed, life itself, are truly made. These silent collapses don't add much, if any, enrichment at the moment of death. They mostly remove material from the cosmos, locking it away behind the event horizon of a black hole. It's a cosmic removal service, rather than a distribution network. This profound shift in understanding has ripple effects, forcing astronomers to refine their models of galaxy evolution, the formation of stars, and even the very abundance of the elements that comprise everything around us, including ourselves. We began with a mystery, the star that was there one day and simply gone the next. The specific fate of the star in the Kinman Dwarf galaxy remains a cosmic cold case, an open investigation. Was it a silent collapse, or is it merely hiding behind a temporary veil of its own cosmic dust? We may never definitively know for that particular star. But that single baffling case has led us down a rabbit hole of discovery. It pushed us to look for other evidence, and we found it. We found other candidates, even if complicated, like N6946BH1. And most importantly, we found the damning evidence of a quiet birth in the perfectly circular orbit of VFTS 243. We now have compelling evidence from multiple angles that stars don't always go out with a bang. Many of the universe's most massive stars may instead die with a whimper, imploding silently, invisibly, into black holes. It's a humbling, and frankly, an eerie thought. It makes you wonder, as we gaze up at the vast, star-filled night sky, how many of those brilliant points of light are not destined for a spectacular, fiery farewell, but are instead silently waiting to slip away into the dark. What else are we missing, right before our very eyes?